Hello! Integral transforms is the topic of today's lecture. And what can I say about integral transforms other than merely murmuring the words in an undergraduate class is usually sufficient to let rip with the most appalling screams of anxiety. So those of you who are here this evening, or those of you who are watching online, I congratulate you for your enterprise and bravery in putting up with integral transforms. The reason I wanted to talk about them is because in this series we're talking about inventions and secret components of IT systems, and integral transforms are a vital key to the way modern IT works. But very few people really know how they work. So what I want to do is to take you through some of the mathematics and theory of integral transforms. I'm well aware that some of us, and maybe even me, will get lost on our journey through integral transforms. So if that's the case, don't worry, don't just mop your brow gently, and the next slide will come along and we'll pick it up. So when watching a mathematics seminar, it's not always easy to focus. In fact, I remember speaking to a professor of maths, and I said, how much of that seminar do you understand? And he said, well, I never understand maths seminars. I don't really understand them until afterwards. So if you don't understand this seminar, then there's my excuse. Right. So for those of you who remember your sort of high school physics, might remember this circuit, which is called a potential divider. And I wanted a little example that gets us started. And the example that I was going to think of was something called impulse testing. There's an old engineering joke which says that in engineering, that if something moves and it shouldn't move, then you should use gaffer tape. And if something doesn't move and it should move, you should use a hammer. And those are the only two tools you need for engineering. Well, the hammer is what we call an impulse. It's a blow and is used as a way of testing things. And this box is known as a potential divider, and if the boxes contained resistors, as they do in this case, then you might remember from your school days this little formula, which is that the ratio of the voltage out of this thing to the voltage into it is given by the ratio on the right-hand side there, which is the ratio of the two resistances. And a resistor, of course, is a device which is the voltage across it is proportional to the current going through it. Now, if I replaced one of those resistors with something that looks like this, then that funny-looking thing there is a capacitor. Don't panic if you don't know what a capacitor is. This is not going to be a circuit theory lecture, so just bear with it. And my point really is that in order to describe this circuit, it's not as easy as just dividing some resistances. The capacitor has a response that depends upon the rate of change of voltage across it. So the current flowing through it depends upon the rate of change of voltage, and we call that dV by dt. It's just a bit of mathematical notation, multiplied by a number called C, the capacitance. So the bigger the capacitor, the higher the current that flows through it. So now we've got this rate of change of something, or gradient. Our very simple bit of circuit analysis has got, well, it looks a bit more horrifying, really, because it's got a derivative in it. It's got this rate of change. And this thing over on the right-hand side is called a differential equation. And I think it's fair to say that undergraduates, on the whole, are not at all keen on such things. And it's probably also fair to say that professors, however, are very keen on them. And there are several reasons for that. I mean, partly it's because solving differential equations is something that can demonstrate your prowess at mathematics, and professors are very keen on doing that. And also, each solution of this depends upon the type of voltage that we're going to put into it. So there's a sort of infinite number of lectures that can be given. We just pick the input voltage. So if we picked a sine wave, then that would have one solution. And if we picked a cosine wave, that would be a different solution. If we picked a step function, it would be a different solution. If we picked an impulse, it would be a different solution. And you can imagine this is very popular in undergraduate lecturing courses because we essentially pick one of these inputs and then we spend between half an hour and 40 minutes on showing people how to solve differential equations for those conditions. And this is good if you like torturing undergraduates, but it has a slight downside if we're trying to design things, because we're going to have to sort of re-solve these differential equations each time we get a different input. So if, for example, the input looked like this little pink line here, which is something called a step function, looks a bit like that, step, sometimes called the Heaviside unit step after Oliver Heaviside, the Irish mathematician, then the output of this circuit looks like this blue line, which is exponentially increasing. So that one way of thinking about that, if you're a physics sort of person, is to think about the capacitor charging up. And it depends on the input voltage, but it also depends upon something called the time constant, which is how quickly the current can flow into the capacitor, and that's governed by how big the capacitor is and how big that resistor is. So it's got this e to the minus t form in there with some additive and multiplicative constants. Now, what to do if I had a more complicated waveform in here? Well, as I indicated, I'm going to be sort of pretty much sort of lumbered doing that. So, because I'm going to have to solve a whole new set of equations. So one thing I might do is I might say, well, these exponentials seem to appear a lot in circuits. So why don't I just sort of solve for a sort of generic exponential? And this is what I've done here. So this on the top here is my differential equation. And here I've just assumed a waveform, a voltage, that is of the form e to the power st. So that's an exponential. And the nice thing about e to the st, I'm afraid I've missed it off there, but I should have put it in there, is that the derivative of that is just multiplied by s. And with a little bit of algebraic jiggery-pokery, I've converted this into a nasty-looking thing, into a nice thing which is easily soluble. And in fact, with a little bit of algebraic manipulation, which no need to follow, I can get it almost into the form I had for my potential divider. Instead of a resistor here and here, as I had in the previous case, I've got something called Z. And Z is something called an impedance, which is a frequency varying resistance. And in this case, it's specified in terms of this variable S, which I haven't said what it is, but it's that exponent in the exponential. So something rather beautiful has happened. It might not be sort of obvious. It might look a bit ugly to you, but from my perspective, it looks rather sort of attractive, which is I've managed to make an assumption about the waveform here. And when I make that assumption, my nasty differential equation becomes a simple little polynomial equation, which I can solve or manipulate in a sort of using my high school mathematics. It's a very, very attractive idea. Now, you might protest at this point, and you might say, well, hang on, Richard, I mean, e to the st, I mean, it's all very well solving for that, but what about the general case, when I've got all sorts of other waveforms that I might want to solve for? Right, well, I've got two things to say there. The first one is there's a good trick in linear time-independent systems, which is something called superposition. And superposition is a wonderful trick that we use a lot. And the idea behind superposition is to think of the circuit we're analysing as a sort of black box. So in this case, I've got some signal coming in, which I've called V in, and I've got some signal leaching out, which I've called V out. And I've said, well, the output voltage here, or signal, is some function of the input voltage. So if my input signal was x of t or something like that, then what would come out is some function of x of t. If it was y of t, then what would come out is some function y of t. And superposition says that if my input signal could be written as some constant multiplied by x of t plus some constant multiplied by y of t, then my output can be written as the sum of the component outputs. Now, that might not seem terribly useful, but it's super powerful because it means we don't have to analyse big complicated waveforms if we can break them down into components. So if we could break this complicated waveform input into additive components, so it's a bit of this plus a bit of this plus a bit of this plus a bit of this, then we only need to find the solutions for each one of those components and then add them back up at the output. So that's the first little bit of usefulness. So if I could express a waveform as some sum of e to the st's, then that's great. I've solved that a few slides back. So all I need to do is add up the outputs. Right, so how could I convert a waveform into some sum of e to the st's or e to the minus st's or something like that? Well, why don't I measure how alike my waveform is to that waveform? So how could I do that? Well, one way is to multiply a waveform by the thing I'm interested in measuring its alikeness to and then average it. So this is what I could do here on the top here. That's me writing that in sort of in simple maths. So this is the waveform I'm interested in. This is the thing I'm going to measure it against, e to the minus st. I've put a minus in there to stop this thing shooting off the slide here. So this is my e to the minus st waveform on the top here. This is the thing I'm going to measure it against. So let's just multiply those two together. And then what I want to do down here is just average all of this. And in mathematics, we normally write that like that. That's a big elongated S on the left-hand side, running from 0 to infinity. Stands for a summation or integral. Don't worry, this dt here, they always go together as a sort of brackets. So I've said 0.63. I mean, I should have written query. I don't know quite what it is. But the idea here is multiply the two together, average it in time, and that measures how alike I am to my prototype here. This is usually called a kernel. Not a kernel as in a military kernel, but a kernel with a K. Right, so I can put those two things together now. And that gives me something that looks pretty horrifying, but I'm going to break it down for you, called the Laplace transform. And the Laplace transform is merely a measure of how alike some waveform, which I've called f of t, is to a kernel e to the minus st. So that is my time domain function or waveform. That's the thing that's probably the input to the circuit or system. And then this thing here is the kernel. And then these two things here, that's the averaging. And it's also worth thinking about what I get as the output. And that output doesn't depend on time anymore. This waveform here depended on time. This one doesn't. It depends on S, and S was a parameter of the kernel. So at a sort of simple algebraic level, this is a bit of maths that takes something that depends on time in one side and something that depends on S on the other side. That's why we call it a transform. It moves from one domain, as we call it, the time domain, into, in this case, the S domain. It's called the Laplace transform after Pierre Laplace. And if you're sort of freaking out about integrals and worried about all these sorts of things, and well you might, because these integrals can be a bit tricky to invert actually, then we often use this curly symbol L. So take a signal, put it through the Laplace transform, out comes f of s. And although I haven't proved this, you can go backwards. So we often use this double-headed arrow. Now, something great has happened at this point. I've now got a magic bit of maths that can convert signals into the S domain. I've sort of indicated that circuit analysis, by which I mean electrical circuits, but we could also be talking about mechanical circuits, can be analysed quite easily in terms of the S domain. And the output, well, if we want to get back to the time domain, and you might think, well, of course we want to get back to the time domain, we can just apply the inverse transform. The inverse transform can be tricky to compute, but usually engineers use a sort of table lookup. So they say, well, oh, it's one of those, right, it must be one of those then. Actually, a lot of engineering never bothers to convert back to the time domain. Engineers, particularly electronics and control engineers, usually do their thinking in the S domain, and they usually won't trouble themselves with explicitly working out the time domain. There's no need, because they can visualize in the S domain, in the transform domain. So that's the essence of an integral transform. It's a bit of mathematical jiggery-pokery that makes the analysis easier. And that sense is probably, fairly sort of standard fare for a lot of engineering and physics courses. Physics courses usually don't really go for the Laplace transform. They're usually into a different set of transforms. But there's a whole book of these, and first time at the end we can try and think of some. But pretty much any problem that you can think of will have an appropriate transform. The Laplace transform is very favoured by control engineers and electronics engineers, circuit design specialists. Nowadays, of course, we tend not to be designing a lot of analog circuits. We're often working in the digital domain, and in the digital domain, we tend not to have differential equations. We tend to have difference equations. Those are just differences of things. Well, there's a transform for that. There's a transform for everything, and that's called the Z transform. Bizarrely, the Laplace transform wasn't invented by Pierre Laplace. The Laplace transform was probably invented by Niels Abel, I think he's a Norwegian mathematician. And Laplace probably invented the Z transform in a bizarre sort of twist of fate. So I don't want to say too much about the Z transform, but that's the method of choice for designing digital filters and for worrying about the stability of objects. Now, I should say at this point that we're really talking about these mathematical tools as the way a mathematician would, as a way of sort of either making problems easier to solve. I mean, you might not feel they're easier to solve, but once you get the hang of these things, they're fairly sort of manageable and manipulable. Or a way of understanding, a way of sort of analysis. But that's not really, well, computer science has some of that, but I think I would also like to talk about these as sort of computational devices. And that means switching across to the sort of the king of transforms, which is the Fourier transform. And I haven't written down the integral form of the Fourier transform because it's got a complex number in it, and I felt that was probably a step too far amongst civilized company, and it's not necessary, because once you've got the idea here, instead of e to the st, we have something that depends upon omega, which is the angular frequency, or if you prefer, f. F is the non-angular frequency, the frequency that we refer to. F is measured in hertz, and omega is measured in radians per second. They're coupled by 2 pi, so omega equals 2 times pi times f. Now, the Fourier transform is, I called it the emperor of transforms? It's the transform that almost everyone knows about, but probably doesn't know about. So they're familiar with the output from the Fourier transform, but they're probably less familiar its computation. So let's just have a look at a few of those and try and sort of get a handle on how it works. So probably the simplest thing I could think of was to refer to the sort of start of a lecture, which is thinking about impulse testing. So that's an impulse is where we hit something with a hammer, or in terms of a voltage, that's where we just sort of ping it with a very short pulse. Here I've used a formulation which is a theoretical one, where instead of drawing a little pulse, I've drawn this little arrow here. And this is an example of an idealized pulse, which it doesn't really exist, but it is mathematically convenient. So the little arrow is something that's meant to represent a pulse that's infinitely thin and infinitely high. So it has an area of 1, but it's as thin as you can make it and as tall as you can make it. They're often called generalized functions, and this is an example of a generalized function, or also called an impulse, but also sometimes called a Dirac delta function, named after Paul Dirac, the Bristolian engineer turned theoretical physicist. And over on the right-hand side, I've plotted its Fourier transform. Some people would call this the spectrum. So let's just have a look at it. So I've got this highly localized thing in the time domain, beep, click, right? And it contains all frequencies over here. So that's one of the reasons that impulse testing is often spoken about, particularly in mechanical engineering, because if I tap something with a hammer, it excites all frequencies in the system. So in the old days of steam trains, there was somebody who went around with a hammer tapping wheels of steam trains, the idea being that provided an input that contained all frequencies. So if there was a defect in the wheel, then there would be enough spectral energy in the impulse to excite that defect, and the skilled operator could listen to the ringing associated with the wheel and know that there was a defect. Such people are known as wheel tappers. Let's have a look at this. Let's have a look at something that's a bit more realistic. So here is the Fourier transform of a pulse. And this is a rectangular pulse centered around time 0. So it's 0, goes up and comes down again. And this is its Fourier transform. Now, you might be slightly irritated to see frequency positive and negative. This is an artifact of the way most people define the Fourier transform, and for all practical purposes you can just focus on the positive frequency part here, and that's what you would see if you had a spectrum analyzer in front of you, only the positive frequency. It's a mathematical artifact having these, and in fact it's not necessary. You can define a Fourier transform that doesn't have them, but convention has it that we have them. And you can see here we've got something. This is called a sine x over x function, a sine f over f function. We've got quite a bit of low frequency energy here. That's associated with this being lifted off the 0 line. And then we've got these side lobes down here. So high frequency, there's not much energy. The energy there is associated with these rapid transitions here. If I were to pick a slightly different shaped pulse, say a longer pulse, you might expect that it would have more energy focused at low frequencies, which it does. If I was to pick a shorter pulse, then you might expect it to have more energy at the higher frequencies. So can you see, if I was to make that pulse thinner and thinner and thinner and taller and taller and taller, this would become wider and wider and wider until eventually it would be flat, which was the situation we looked at in the previous slide. So that's, in fact, that is usually the proof of the impulse at 0. So in reality, your wheel tapper doesn't manage to excite all frequencies because he or she is only able to tap the wheel for a finite amount of time with a finite amount of energy, and so we have this shaping here to the spectrum. Now, to engineers and analysts, you can work in this domain or you can work in this domain, you can work in the time domain or the frequency domain, and everything is spiffy. If I picked something that was well matched to my Fourier transform, like a cosine or a sine wave, and the Fourier transform can be written in terms of cosines and sine waves, then I get two generalized functions in the frequency domain. So this is a cosine wave of frequency f0, and it has a spike, infinite height, zero width, at f0. So the Fourier transform is particularly well suited to oscillating waveforms like cosines and sines, and that's one of the reasons it's popular, because a lot of things tend to oscillate go up and down in nature. Right, well, so far so good. I still haven't really got past the sort of using the Fourier transform as a tool for understanding an analysis. And in fact, you might be feeling your understanding is slightly worse than it was at the beginning of this because of the mathematical complexity associated with transforms. But I want to just do one more little diversion, and then we'll get on to it as an algorithm. And that relates to randomness. Of course, in reality, signals are most likely to be random. And up to this point, I've been talking about signals that are defined by a simple equation. But the reality isn't like that. You know, the reality is I might have some waveform like this, which is actually me saying the words Gresham, I think, if I remember rightly. So how could I handle that? Well, the Fourier transform can certainly be used, but it isn't used directly on the time domain signal. It's used on a measure of how alike the time domain signal is with itself. We call that autocorrelation. And the way we work that out is to use our trick of multiplying and averaging again, except we multiply the signal by itself. So we shift the signal by, in this case, an offset called tau. We multiply the two together, and that particular shift here is associated with one value here at a particular tau. And then we just shift this thing across here, and as tau varies, we create this thing here, which is not time along here, this is delay, sometimes called lag. And if we take the Fourier transform of the autocorrelation, then we now have something that we can work with, and that is usually known as the power spectrum. It's not quite the same as the spectrum that we've been dealing with. It has different units for one thing, but it has the same sort of intuitive idea, which is these features here relate to components of interest in the signal. And when people are talking about, well, talk is often quite loose on what's meant by these things, but when people are talking about a spectrum, then that's usually what they're talking about. They're talking about something that is technically the Fourier transform of the autocorrelation function. Now, in reality, computing the autocorrelation is a bit of a pain. There's some technical reasons for that to do with convergence, but there's also a practical reason, which is you've got to sit. It looks like a sort of batch process, doesn't it? You have to sit there, measure the signal, shift it around with a copy of itself, multiply it together, do all those integrals and add it up. So in reality, you might not want to do that. So there are various approximations in which you split the waveform into little chunks. You apply the Fourier transform to those little chunks, and then you do some averaging over those chunks, and that can also be shown to produce the power spectrum. In fact, there are whole theses written on methods of estimating this statistic from the original time waveform without having to go through the tedium of computing the autocorrelation to get there. Right. Looks like a bit of a pain to compute this. we have to do this thing called an integral, and we have to do it for every possible value of frequency. So if you think back to that equation for the Laplace transform, if you imagine writing a program to compute it, you would think, all right, so I've got to pick a particular s, right, get my e to the st, right, draw that out, multiply it by the time waveform, do the integral, average. Right, that's one value. Right, new s, stretch it. Looks very tiresome indeed. So there's an approximation that we use to that Fourier transform, which is the Fourier transform applied to signals that are already discrete. Discrete here meaning separate. C-R-E-T-E, that sort of discrete, not E-E-T. And this is it. It's the discrete Fourier transform. And you might sort of think, well, gosh, this doesn't look very much like what we had previously. Actually, it does have almost identical form with a few constants knocking around different in each case. So the first part of this is the signal itself. And that's there. And I've called it a time domain signal. And you might say, well, where is time? Well, because it's sampled, because it's discrete, I'm using n to index it rather than t, but it's the same thing. So it's the sampled thing. And I'm multiplying it by something. That's the thing I want to measure how alike it is to. And I'm calling that the kernel, just as I did with the previous thing. And because it's a discrete signal now, I'm not going to do an integral. I'm just going to do a summation. So that's that bit there. And once I've done that average, I called it an average. You might moan that I should be dividing by n for it to be an average. Well, let's not worry about divide by n's, divide by t's, you know. It doesn't really matter. I should say, and then over on the left-hand side, I've got my transform. And the thing about the transform is it doesn't depend on n. N has been summed away, if you like. It only depends on m, and this is the equivalent of frequency here. Now this is the master work of modern computer science. This is the discrete Fourier transform. It's the discrete version of the Fourier transform. I hesitated a bit there over the divide by n and all those things. It's probably worth saying that in old books there are quite a few different definitions of Fourier transforms, and they differ a little bit in some of the symbols and some of the normalizing constants. There are some 2 pi's that skulk around the place, and some people want to divide by root 2 pi so that the inverse transform and the forward transform look the same. Doesn't really matter. Nowadays, there is general agreement on where these constants should sit, and that's the definitions that those are the definitions I'm using here. Right, so this thing is the algorithm that dominates modern computing. And I'll demonstrate, I'll try and explain why that is in a few moments' time. So let's just spend a short while just trying to understand what it does. So if I apply the discrete Fourier transform, or DFT as it's almost always called, to a discrete version of the cosine wave, which is what I've drawn here. So this is a cosine wave. You can see it's a cosine wave because it starts up here at its maximum value, and then it goes up and down, and it ends just here. And I've chosen a cosine wave that fits absolutely perfectly into the number of samples I have in my little graph here, which happens to be 1,024. And you can see the output. It looks a bit weird, but I'll explain that in a moment. Firstly, there is a spike here, and that is at the frequency of this cosine wave. This spike here looks a bit odd. The way this thing is formulated is these are all our positive frequencies up to around 512, and then these have to be wrapped around over here. These are the negative frequencies that we were looking at, and I said not to worry about. So just for the time being, just consider this bottom part of the graph. So that looks, well, pretty fab and groovy, really. I mean, you've got to compute it, but it gives a reasonable approximation to what we're expecting. It's not a Dirac delta, great big infinite spike, because we have a finite amount of data here, so we don't get an infinite amount of, don't get an infinite spike, we get a finite spike, but it looks a bit like what we would expect. But because it's a discrete algorithm, there are some nasties which we always seem to have to take care of. Here's one. If I just change the frequency of this waveform a little bit, what you might expect is that this spike would move this way or this way, left or right, depending on the frequency. But in fact, that does happen. But what also happens, if I do that, is some artifacts appear. I'm not sure if you can see them on the slide, so I've just sketched them in here. They're called leakage, spectral leakage. And the spectral leakage is caused by the fact that this waveform here at the end doesn't exactly line up with the start. I didn't make this evident, but it's an artifact of a discrete Fourier transform that it makes an implicit assumption that the waveform is repeated out of the interval exactly. So when we choose a frequency that doesn't exactly fit into the interval, we create what look like big jumps. These cause spectral energy, which causes imperfections, known as spectral leakage. Well, there are whole books written on ways to avoid spectral leakage, but the standard way is to force the issue. And the way you force the issue is by multiplying the input waveform with something called a window. Okay, so this is one that forces the ends to zero. So if you force the ends to zero, obviously this thing lines up and the spectral leakage disappears. It does have a consequence, which is as we squeeze those ends down to zero, we broaden the peaks. Perhaps I should have said this when I was talking about that rectangular pulse. I don't know if you noticed, but as the rectangular pulse changed width, the width of the sine x over x function also changed in exactly the opposite ratio. So that's something called the time bandwidth product, which is always constant. And if you were a physicist, you would say, yes, well, I know that position and momentum are Fourier transform pairs, and I know, due to the Heisenberg uncertainty principle, that position times momentum is always a constant. So in other words, you can know precisely where you are, but not know how quickly you're going, or you can know precisely how quickly you're going, but not how precisely where you are. Always a good excuse if you're stopped by a policeman on the motorway and you're a physicist. And the same thing applies in everyday life. So you can either know precisely where you are in time, but not know the frequency very precisely, or you can know the frequency precisely, but not know where you are. And it's a consequence of the finite window of analysis, which we're seeing in this case. So there's a whole sort of sub-genre associated with using the discrete Fourier transform in an elegant way. Now, I should say that you've probably heard that the term DFT, discrete Fourier transform, isn't actually used that much nowadays. Almost everyone would use the term FFT. And the FFT stands for fast Fourier transform. It always used to stand for one algorithm, known as the Cooley-Tukey radix 2 algorithm, but there is now a whole library of fast Fourier transform algorithms. So when people say the FFT, they could mean any algorithm for computing it quickly. And I may have used them interchangeably in this lecture, and if I have, I think that's now acceptable. If we were an undergraduate lecture, I'd be saying, no, they're completely different. But I think in common parlance, nobody computes a DFT the slow way. Everybody computes it using one of the numerous fast algorithms there are out there. The fast algorithms arise because the kernel function in a Fourier transform rotates. And because it rotates, we can find symmetry in the algorithm. So we can split the multiplications associated with the kernel function into multiple separate multiplications, and that gives us computational efficiency. Right, let's look at some examples of how it's applied, because I want to sort of dwell a bit on how the FFT, the DFT is used. And the first example of this I've picked is something I've been longing to talk about for quite a few lectures, and I realise I should have talked about it in my compression lecture, but there just wasn't enough time. So I've sort of snuck a bit of compression into this lecture, partly to sort of fill a hole that I felt needed to be filled. This graph, which is quite an old graph now, talks about the response of the human ear. And we're describing an effect here known as masking. And masking is a property that arises from the way the human cochlea, which is the human Fourier transformer that's in your ear. That's how it works. And the human ear is incapable of hearing certain things when certain signals are present. So, for example, if a signal falls below this smooth threshold here, labelled threshold in quiet, then we probably won't hear it at all. If you can't read this, on the bottom here we have a frequency axis measured in kilohertz, and up here we have sound pressure level measured with respect to some reference. I can't remember what the reference is. There's also, I don't know if you can see this, but there's a second graph here, and this threshold arises from the presence of a tone. So if we had a tone, which I've sketched here as a Dirac delta symbol, if we had a tone here of this intensity, then any signal that falls within this is not going to be distinguishable by human ear. So if you think about the signals that you're used to listening to, if there is a substantial tonal component of, say, a music signal, let's say you're listening to someone playing the violin, so maybe the fundamental or the second harmonic of a violin dominates what you're listening to, there are other bits of the musical signal that you can't hear. So there's clearly some potential there for not sending those across the airwaves or onto the disc at all. And that's the basis of what's called lossy compression. Lossy compression is when we're prepared to completely eliminate parts of the signal because we think the other end, won't receive it. So several important points there. It's the human, the other end. So if your dog is listening, I'm not so confident because we don't know how dogs and cats and non-humans work. This is a human-only system. So if you are listening to or sending compressed digital audio, and you almost certainly are doing that, well, certainly during the duration of the pandemic, if you were on Zoom, as most of us were, or Teams, most of us were virtually every hour of the waking day and several hours of a non-waking day if you're working with other countries, you were doing this every single moment. And what you were doing was following something like the MP3 coding standard. And this is a diagram of it. There are different acoustic standards, but the MP3 one is sort of canonical, and the basic idea is repeated around and again and again. And what I'd like to draw your attention to here is we've got this digital audio coming in here. The first thing that's happening over here is a fast Fourier transform algorithm. Well, we just talked about that. Then we're running this model. So what the model is doing is it's looking for these spikes, and it's trying to work out what the masking threshold is. And having worked out what the masking threshold is, it's then going to use more or fewer bits to code bits of that signal. Now, it has to do that, it has to do it in the frequency domain and not in the time domain. So this part of the algorithm up here, top left, splits the input signal into subbands, right? it then transforms them, usually using a modified discrete cosine transform, which is a type of Fourier transform. It then applies a different number of bits to each one of these bands. It then does some standard run length encoding and compression and slams it out down the audio stream. So if you're listening to digital television or digital radio, or you're listening, or you're broadcasting via Zoom or Teams or whatever you're using, you're doing something like this. And the rate that you're doing this is fairly amazing. You're doing this at probably, well, if it's high quality audio, 44.1 or 48 kilosamples a second. So you're doing a lot of it. Now, this is one of the algorithms that fall, I think, in the discrete Fourier transform, or FFT, Hall of Fame. And I'll talk a little bit about some of these now. But before I do that, I thought I'd draw your attention to this quote from Gilbert Strang. Strang is a sort of bit of a hero of undergraduates for his explanations of matrix maths and linear algebra. And he has described this as the most important algorithm of our lifetime. And let's just talk about some of these briefly. So audio coding we've talked about. The idea there is that the FFT is certainly used for computing the psychoacoustic masking. It may, in some versions, also be used for the subband filtering, filtering into bands and applying, then subsequent to that you're going to apply a different amount of bits. Not all standards use that. Some use filters, some use the DFT. Video coding I have talked about in previous lectures, but if you're watching this online, you're not watching the video that you're watching has been split into 8 by 8 pixel blocks. Those blocks have been transformed using a version of a discrete Fourier transform with the discrete cosine transform, which is tuned to all positive values of the sort that you get in images. Then some of those coefficients are sent, but others are discarded because we don't think the human eye can look at them. And in previous lectures, I've certainly looked at how the DCT does that. So not only was your Zoom call, was the audio coded using the DFT, the video was coded using the DCT, which is a type of Fourier transform. Speech recognition, there are various ways of doing speech recognition, but one of the standard ways, and I think I discussed this in a lecture a few years ago, are to use Mel frequency Kepstrel coefficients, and MFCCs as they're called, are a measure of how the spectrum of the audio changes, or what the shape of the spectrum is. And the way they measure that shape is rather interesting. They use, first of all, the discrete Fourier transform to compute estimates of the spectrum in blocks, and then they measure the spectrum of the spectrum. So they apply the Fourier transform to the spectrum to work out that shape, and it's the spectrum of the spectrum, or Kepstrom as it's often called. Kepstrom is a little joke where you interchange some of the letters to indicate that it's a slightly different form of spectrum of the spectrum, to characterize the voice. One interesting thing about speech recognition, of course, is that it has to happen continuously. So we can't, it's no good sort of waiting a goodly amount of time computing everything. We have to do it now, otherwise there's too much delay in the system. So speech engineers divide the speech into little blocks, usually 20 milliseconds. They compute the DFT in a block, and then they overlap. So they wait 10 milliseconds before computing another block, and another block, and another block, and another block. So there's always this overlap. They use windows that exactly overlap. So in principle, you could add them back together and get the original waveform. So they use this overlap idea, and that allows them to either do recognition or speech coding. The overlapped transform that is particularly tuned to being able to add them back together in an easy way is known as the modified DCT. It's the system they use for that, or MDCT, which again is a form of discrete Fourier transform. Digital TV, well, we've talked about digital TV, the coding, but the FFT is also used in the transmission, because they use, and as does cellular telephone transmission nowadays, 5G uses something called OFDM, orthogonal frequency domain multiplexing, or modulation, modulation, I think. And the way that works is they say, well, it would be very convenient if the frequency band we had available wasn't completely used by one person. So we want to split it into very precise little subbands, and we want, say, Bloggs' phone to go down this little band, and Keith's phone to go down here, and Vera's phone to go down this one. Right. But we want to be able to do this adaptively, because sometimes we're very busy and we want to restrict people's access, and sometimes it's not so busy and we don't mind having that. Is there a way of doing this? Well, what they do is they say, right, well, we would like to put them onto little carrier waveforms, and we'll multiply those carrier waveforms by the signal from, say, Bloggs. How can I do that when I'm not quite sure what the carriers are and they're going to have to vary, and when I'm overseas it's different? I know what I'll do is I will use an inverse DFT to create all of these. So I'll multiply the signal by a sine wave, and then I'll put them into an inverse DFT and create a time waveform that is essentially the sum of all these little channels. So your mobile telephone is doing a discrete Fourier transform as often as it can. In fact, one of the reasons your mobile phone gets hot, and one of the reasons why your digital TV gets hot, is because there's a chip in there just hammering out the discrete Fourier transform without halt. Okay, I haven't really got time to talk about these other applications, but there's an awful lot of them. But I just wanted to mention one that, well, once you get to a certain venerable age, you start to worry about various things, including your health, and health is always popular, so I thought I'd quickly talk about the connection with one of these things. So this is, actually, I think I was going to say it's a CT scanner. I think it might be an MRI, but it doesn't really matter. The idea behind these things is that on one side of your head, or body, is something that transmits something, maybe some ionizing radiation or non-ionizing radiation, and on the other side we have a receiver, and they rotate around. You can hear them rotating as you sit in these things. So over on the right hand side here is the basic idea. We've got something that's rotating, and what we measure is the total transmission through the body. So we're not quite measuring, you can't really do very much with this. This thing is usually called a sinogram. And this thing on the right-hand side, the sinogram, is actually another form of integral transform. It's called a radon transform. And the way you, of course, you've got this thing on the right-hand side, and you would like this lovely picture on the right. You would like to see into your brain or see into your pancreas or whatever it is you're imaging. And so you have to solve this inverse transform problem. I haven't talked much about inverse transforms, and that's because the mathematics is a bit more complicated. But in order to solve the inverse radon transform problem, you usually use the discrete Fourier transform. Yes, it even appears in medicine. So you take the Fourier transform of this sinogram here, you multiply by wave number, which is the spatial equivalent of frequency, take the inverse FFT, and that's when you get a picture of your brain. So the next time you're lying in one of these things, feeling a bit scared for your life and wondering what the hell's going on, you can engage the radiologist in entertaining repartee about which Fourier transform algorithm they're using and the windowing that they used in order to get it looking good or not, as the case may be. Now, I can see time is pressing upon us. I did want to say one thing, though, which is the Fourier transform is a rather interesting thing, and it's well understood by physicists and engineers and is part of the syllabus. It isn't part of the syllabus for computer scientists and programmers and software engineers. They may know it, they may know something of it. But for a lot of people, the understanding is probably a little bit less than a black box. It's a thing you put numbers into and out come some other numbers. So that's a bit of a concern to me because it's far more than that. And in fact, there are simple tests you can do to see that it works. And we've talked about some of them here. If we put in, say, a spike, then we should expect to see all the numbers come out equal. If we put in a cosine wave, we should expect to see spikes come out and so on. It's quite easy to be intuitive about what these things are working and whether they're working or not. And that's an increasing issue for modern computers that bothers me a bit, that there's a sort of black box approach to design and understanding, which means it's difficult to be confident that the system you're using is in fact doing what it's meant to be doing. The Fourier transform is perhaps the most low-level box I could think of. It's probably the lowest level box that isn't understood by most people that I could think of. But there are others. And the others, you could sort of wrap up into that interface between the real world and the thing that you're doing on the real world. And that interface with the real world in a computer system is usually called an operating system. And so that is the topic of the next lecture, and in fact will be the topic of my final lecture. Thank you.
Thanks so much, Professor Harvey. We've got a couple of questions from the online audience, which I was going to start with, and then we can move on to the audience in the room. The first question is, why is the length of the FFT always a power of 2?
It's not. It always used to be, because there was only one algorithm for computing the FFT quickly, and it was called the Cooley-Tukey algorithm, and it worked in powers of 2. Worked on lengths of signals of powers of 2. Nowadays, there are plenty of other choices, prime number transforms and so on, and there's whole books of these choices, so it doesn't need to be a power of 2. So it's pure mystique that it is a power of 2. And perhaps what the questioner means is, why the hell did you pick a power of 2 to demonstrate it? And I don't know the answer to that. I should have picked something that wasn't a power of 2. Second
question from online, what is a spectrogram?
Spectrogram. So the Gresham College illustrated this lecture with a spectrogram, actually. And a spectrogram is a set of DFTs taken one after another and displayed using pseudo-colours. So they're very popular with speech engineers, and they're used for, a friend of mine can look at the spectrogram and know what was said, which is a wonderful trick. If you'd like to know more about spectrograms, then there's an online lecture from me on speech recognition called How to Wreck a Nice Peach.
Thanks so much, Professor Harvey, and please do come to the next lecture on the 31st of May at 6 o'clock on operating systems. Thank you so much.
Thanks.